Hayashi-san from YITP, who is going to tell us about bridging two semi-classical confinement mechanisms, monopoles and center vortex. Please start.
Thank you. Thank you for the introduction. And I'd like to thank the organizers for giving me this chance. And thanks everyone for coming. I'm talking about semi-classical understanding of confinement. And this talk is based on this work in collaboration with Yuya here. Okay, so let me begin with quick historical review on confinement mechanisms. There are two famous scenarios, traditional scenarios for quark confinement. One is monopole condensation scenario, and the other is a center vortex proliferation scenario. And where the first one, the monopole condensation scenario, is known as the dual superconductor picture, where we suppose that magnetic monopole condenses at the vacuum, and then through the dual Meissner effect, quark and anti-quark fields linear confining potential. The second one, the center vortex proliferation. The second one is the center vortex proliferation, and the center vortex is where vortex-like configuration, which rotates the phase of linking Wilson loop by a center element. That is where a center vortex is codimension to defect-like configuration that carries the 1/n fractional magnetic flux. And if such excitations proliferate, then the phase of the Wilson loop would become randomized. Then the Wilson loop average will decay faster as we grow the size of the Wilson loop. And typically, it decays at the area low. By the way, you can understand this scenario as a restoration of the N1 form symmetry that is caused by proliferation of codimension 2 objects. This is an analogy with the phenomenon that discrete zero form symmetry can be restored by proliferation of domain walls, codimension 1 objects. Then in analogy with this, discrete one form symmetry can be restored due to the proliferation of codimension 2 objects. And with this perspective, this scenario would be natural. So these two are very old intuitive understanding of confinement. And it is natural to ask the connection between them. And there are old works on it. And in these works, it has been suggested that monopole can appear as a junction of center vortices or as a kink of center vortices, because center vortex is a kind of 1/n fractional magnetic flux. So monopole can appear as a junction of them. So this is the old story. And here is a summary of what I'm going to talk about. Well, I've mentioned that the famous quark confiners are monopole and center vortices. And in recent years, there has been an effort to understand the quark confinement semi-classically. I mean, by deforming the SUN Yamil theory or other confining gauge theory into a weakly coupled theories, and study the weakly coupled theory and see how the confinement occurs in that theory. And there are two ways, weak coupling semi-classical realization of quark confinement. And one is a monopole semi-classic setup, and the other is to the center vortex semi-classic setup. And in this setup, we can realize the situation where the monopole gas causes confinement, And in this setup, we can explicitly see that the center vortex gas causes confinement. So corresponding to the old scenarios, there are weak coupling realizations. Then it's natural to ask the connection between them. And in this work, we consider an interpolating setup between this framework and this framework. And we will show that these two frameworks can be smoothly connected, and monopole instanton here and center vortex instanton here are essentially the same. And during this crossover, we can observe how monopole stems magnetic flux. And then we can find, during this crossover, we can find monopole. We can find monopole appears at the junction of center vortex-like magnetic fluxes. This is the outline of this talk. Okay, so we have finished the short introduction, and then let me introduce about these two semi-classical methods, 3D monopole semi-classics and center vortex semi-classics, and then we will bridge them, and then I'll summarize. Okay, so let me introduce semi-classical approaches to understanding confinement. The idea is to deform SUN Yang-Mills theory to weakly coupled theory with keeping confinement. And here we employ compactification to make the theory weakly coupled. And to keep confinement or to keep the vacuum structure, we add some tricks. I mean, we add some center stabilizing deformation when we compactify the spacetime. And in this talk, we focus on the following two methods. In this method, two methods. One is a 3D monopole semi-classics, and the other is 2D center vortex semi-classics. And in the 3D monopole semi-classics, we compactify S1. We consider 4D Yang-Mills theory, but we compactify S1, so we consider SUN Yang-Mills theory on R3 cross S1. And to keep confinement, we add center stabilizing deformation, which I'll explain later. And in the 2D center vortex semi-classics, we consider T2 compact. We consider SUN Yang-Mills theory on R2 cross T2. And we insert soft flux or ZN1 form background on T2. So this is how we compactify. This is how to compactify in these approaches. And the main ansatz of these semi-classical method is adiabatic continuity. Let's vary the size of compactification scale. And when the compactification scale is large, the theory is close to the original four-dimensional SUN Yang-Mills theory. So we want to know this region. On the other hand, at small compactification scale, the theory becomes weakly coupled. So we can analyze here, where semi-classical analysis is valid. And the adiabatic continuity conjecture states that there is no phase transition between them. And if this is true, then you can study the vacuum structure of the original theory through semi-classical analysis as a weak coupling setup. So you can analyze the vacuum structure of the strongly coupled difficult theory through semi-classical analysis as a weakly coupled theory. And in the end, in this framework, in the 3D monopole semi-classics, we can see how 3D monopole gas causes confinement. And in the 2D center vortex semi-classic setup, we can see how the center vortex gas causes confinement. So this is a main story of semi-classical approaches. So I'd like to introduce these two methods, but beforehand, let me add some remarks on the adiabatic continuity, because this is a key assumption of this method. So in this talk, we consider R3 times S1 setup and R2 times T2 setup. So we consider S1 compactification and T2 compactification. And 4-dimensional SUN Yang-Mills theory has ZN1 form symmetry. And under the S1 compactification, then we can consider 3D effective theory. And in terms of 3D effective theory, the 4D one-form symmetry is decomposed to 3D one-form symmetry acting on spatial Wilson loop, and 3D zero-form symmetry acting on the Polyakov loop along S1. And similarly, under the T2 compactification, the 4-dimensional one-form symmetry is decomposed as follows. Because this is T2, so we have two Polyakov loops. So there are two ZN zero-form symmetry. And if we compactify naively, then there is a deconfinement transition somewhere when we vary the size of compactification scale. So if we make the size of the compactification scale smaller, then at some point, spontaneous breakdown of this zero-form symmetry of 3D or 2D occurs, and which is called deconfinement transition. So with the naive compactification, the adiabatic continuity does not hold. And here, then at the compactification scale, it is weakly coupled, but this is the confined phase. So this is not what we want. So to avoid this deconfinement transition, we want to keep this ZN zero-form symmetry. For this purpose, in the 3D semi-classics, we add Polyakov loop potential by hand. And in the 2D semi-classics, we insert Toft flux on T2. That is ZN1 form background. So by adding the center stabilization, we can eliminate this deconfinement transition. Then we can expect the adiabatic continuity. And at small S1 or at small T2, the weakly coupled confinement realizes. So let's study this weakly coupled confinement. And
Can I make a question, or
Okay.
I should ask later?
Please,
you can ask now.
yeah, please ask.
In the three-dimensional case, if you make a compactification to 3 dimensions, naively the flux had extend only a 2 dimension, so that you will have a log behavior of the potential. And so without considering, it seems to me that you need any magnetic monopole condensation. But I wonder if this is related to this Z0 symmetry is conserved or not.
You mean in the deconfinement phase of 3D one form symmetry is maintained, and what is your question?
My question is, when the compactification radius is very small, you have effectively space extending in the two-dimensional world, so that the flux extend only 2 dimension, and naively you would have a log potential, which would make up confinement. This is, you don't need a magnetic flux, magnetic monopole condensation, I suppose.
As
When
far
the
as I
red
can,
when the compactation radius is large, the behavior of the potential is completely different. So that naively, I would expect that deconfinement phase, transition to the deconfinement transition. Is this interpretation has nothing to do with your this symmetry, ZN symmetry preserving or not? Maybe my understanding is too naive.
Well, in the deconfined phase, or you can consider 3D Coulomb phase, then the 3D one-form symmetry is preserved. And yeah, in this case, spatial Wilson loop is the confinement occurs in the sense of 3D Wilson loop, spatial Wilson loop. But if we compactify naively, then Polyakov loops feels deconfinement. Polyakov loops undergoes deconfinement. And this is the phase transition. So the vacuum is not adiabatically connected.
Okay. Thank you.
Okay, thank you. Thanks for the question. So yeah, what we want to know is a vacuum at the vacuum of the original theory. So we want to connect to the weakly coupled situation without phase transition. So yeah, some trick to stabilize the center is necessary. Okay, and before we move on to the concrete analysis of the semi-classics, let me add more on continuity, more remarks on continuity from the perspective of anomaly and symmetry. And there is a famous anomaly in SUN Yamil's theory, that is mixed anomaly between one-form symmetry, Zn one-form symmetry, and theta periodicity. And this is very important. And one could say that this mixed anomaly can be interpreted as confinement implies multi-branch vacuum structure. So we want to keep this mixed anomaly structure. With keeping this in mind, let's see the S1 compactification and T2 compactification. In the case of S1 compactification, the 4D one-form symmetry is decomposed as Zn one-form, 3D one-form symmetry and 3D zero-form symmetry. And there is a mixed anomaly between 3D one-form symmetry and 3D zero-form symmetry and theta periodicity. And in this setup, we enforce to this 3D zero-form symmetry to be unbroken. So yeah, in this sense, this relationship, in this sense, one could say that this relationship is preserved. Okay, so the next, let's see the T2 compactification with Toft flux on the torus. Then the 4D-dimensional one-form symmetry is decomposed as this. And the anomaly relation could be written like this. So here, this term is somewhat important because this term implies if the Toft flux is non-trivial, then there is mixed anomaly between Zn one-form symmetry and theta periodicity. So Toft flux not only stabilize the zero-form center symmetry, but also Toft flux plays an important role to keep this anomaly relation. Okay, I think it is enough to enough for remarks on adiabatic continuity. So let's get into concrete analysis on 3D monopole semiclassics and 2D center vortex semiclassics. As I mentioned earlier, we consider SUN in the 3D monopole semiclassics. We consider SUN Yang-Mills theory on R3 times S1. And to keep confinement, we add center stabilizing deformation. And more concretely, we consider Yang-Mills theory on R3 cross S1 plus some Polyakov loop potential to enforce Polyakov loop to take a center symmetric value. I don't talk about the concrete coefficient of AN, but if we take AN large enough, then the center symmetry is kept for small s1 because at small s1 you can calculate the Polyakov loop potential called GPY potential, and if AN is strong enough to flip the coefficient, then the center symmetry can be kept at small s1. And so we can realize weakly coupled confinement at small s1. If you don't like this double trace deformation, you could also, instead you could add some massive adjoint fermion. Okay, so
I have a naive question. So
Okay.
if AN, even if AN is large,
Hmm.
so AN looks like a kind of coupling constant. Is it still weakly? Gauge coupling is weak, but perturbation is good, or even if AN is large?
If AN is large, then in the 3D description, then the Polyakov loop is just fixed to the center symmetric value. Then after this, you can get weakly coupled theory.
Okay. The Polyakov loop is massive.
Yeah, right.
Thank you.
Thank you. So this is a setup. And so, okay, so we consider R3 cross S1 with small s1. So let's consider 3D effective theory on R3. From the 3D, in the 3D perspective, we have gauge field, 3D gauge field, and we have Polyakov loop, which is adjoint scalar field in the 3D perspective. And because we stabilize the center, it is enforced to take the center symmetric value. And in some gauge, you can write the Polyakov loop is fixed to the clock matrix. Clock matrix is a diagonal matrix with the element 1 omega squared, blah, blah, blah. And for example, for n equals 3, it is this one. And with this adjoint scalar field, the adjoint Higgsing happens. Adjoint Higgsing from SUN to Cartan U1 to the n-1 occurs. So the 3D effective theory is 3D Cartan abelian gauge theory, 3D U1 to the n-1 gauge theory. And because this the reduction occurs due to the adjoint Higgsing, there are monopoles. So the 3D effective theory is abelian gauge theory with monopoles. And for such theories, Polyakov said confinement occurs due to the dilute gas of monopoles. So with this deformation, with this compactification, with center stabilization, then we can cook up the situation where the monopole causes confinement. And let me add something more, some details more on 3D monopole semiclassic on this setup. So I said there are monopoles. Actually, there are n kinds of monopoles here. Usually associated to the adjoint Higgsing from SUN to the U to the n-1, there are n-1 BPS monopoles. And they have magnetic charge alpha 1, alpha 2, blah, 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 which are simple roots of SUN. And reflecting the adjoint Higgs, in this case, the adjoint scalar field is a Polyakov loop, and it is compact. And reflecting the compactness of adjoint Higgs field, there is one more mysterious monopole here called KK monopole with this magnetic charge. And actually, they are fractional instantons with topological charge 1 over n. And intuitively, you can consider these as a constituent of instantons. I mean, if you suppose that one instanton on R3 cross S1, then one instanton can be decomposed into these n kinds of monopoles. Because they have one over n topological charge. Each has 1 over n topological charge, and it has this magnetic charge, and magnetic charge is 0 in total. So one instanton can be decomposed to 1 minus 1 BPS monopoles and 1 KK monopole. So they are the monopole in the 3D effective theory. And you can write the concrete form of 3D effective theory where, because there are monopoles, it is convenient to move to the magnetic representation. So for this purpose, we use 3D abelian duality. And in 3D, the abelian duality maps gauge field to compact boson. And we call this compact boson dual photon or magnetic potential. And in terms of this dual photon, you can easily write the monopole amplitude like this, because monopole alpha I has magnetic charge alpha I, affine or simple root. So after the 3D abelian duality and the dilute gas approximation of these monopoles, then you will get this effective action. This is just a kinetic term, and this term arises from the dilute gas of BPS and KK monopoles. And with this 3D effective theory, you can derive the multi-branch vacuum structure and linear confinement for the spatial Wilson loop. Okay.
Is it possible to compute the amplitude?
You mean the numerical factor of the amplitude? Where the analytic solution of these monopoles are known. So in principle, you can compute. But I don't know how exactly to do it.
What do you mean by the amplitude? Monopole amplitude. What do you mean? Amplitude means just some
statistical weight?
Yeah, just a statistical weight.
So it's the first factor is just the Boltzmann factor associated with
Right.
the action.
Yes. This is a Boltzmann factor, and this comes from the magnetic charge. And if theta is present, you can add here. Well, in the Suji case, you can determine with coefficient, with exact coefficient. So yeah, from this you can, I think from this you can calculate these coefficients. Okay, so let me move on to the next method. It is the center vortex semiclassics where the confinement occurs due to the dilute gas of center vortex. The setup is SUN Yamil theory on R2 times T2 is Toft flux or ZN1 form background. And let me briefly mention how to insert the Toft flux on T2. Or yeah, okay. This is T2, and we identify here and here and here and here. And we want to put ZN defect at the origin. And this can be implemented as follows. This can be implemented to the transition functions from here to here to from here to here as follows. So inserting a unit Toft flux is equivalent to choosing the transition functions so that they satisfy this relation. And up to gauge, actually, you can take G3 as shift matrix or G4 as clock matrix. Then you can satisfy this relation. So you can understand the Toft flux as a twisted boundary condition with shift and clock matrix. So this is how to insert the Toft flux. And there are three important consequences from Toft twisted compactification. First, as I mentioned before, the center symmetry is kept at small t2 due to this Toft twisted compactification. I mean, if t2 is very small, then the fluctuation is suppressed and Polyak flips almost purely, Polyak flips comes almost purely from the transition functions. So classically P3, Polyak flips along here is shift matrix and P4 as clock matrix. And this classical configuration respects GN0 form center symmetry. GN times GN0 form center symmetry. So thanks to the Toft flux, the GN0 form center symmetry is kept to be unbroken, even at small t2. And also, due to this twisted boundary condition, all gluons acquires large Karuta-Klein mass, so they are decoupled. And finally, there is numerical evidence for the existence of center vortex or self-dual fractional instanton as a local solution. Here, local solution means the self-dual fractional instanton exists locally if the boundary condition of R2 is not considered. So since there is numerical evidence, so we jumped to assume the existence of the center vortex and try to calculate the dilute gas of center vortex. And here the center vortex and the anti-center vortex vertex. Here we put the center vortex and the anti-center vortex vertices as this one. K is just dimensionful constant. We don't know what K is, but just try the dilute gas approximation. Okay. Then the dilute gas approximation is this formula, where here, since we are calculating the partition function, so we impose that the total topological charge is integer. Then after exponentiated, then we have this. And this means there are n semiclassical vacua with this energy density. So just by the dilute gas of fractional instantons, you can explain the multi-branch vacuum structure. And also, you can derive the area of fall-off of the Wilson loop, special Wilson loop on R2 from the similar dilute gas calculation of center vortices. This is fractional, but sorry, what is your question?
Fractional vortex.
There are fractional instantons on R2. Yeah, you can say fractional vortex, but yeah, you can say that is fractional vortex. Yeah, the solution is not known. No, solution is not known up to now. So this is yeah, just numerical evidence. So this is one of the problem in the 2D center vortex semiclassics.
There's no size modular. There's no, so.
Size is fixed. Yeah, right. It is determined by the size of T2. Okay, so let me summarize the background materials. Yeah, it is supposed to be self-dual. Sorry. There are numerical solutions on the lattice, but there are no analytical solutions. Okay, so let me summarize the background materials. So there is semiclassical works to deform the SUN Yamil theory to weakly coupled theory without changing vacuum structure, and to analyze the weakly coupled theory to understand confinement. And there are two methods. One is 3D monopole semiclassics, where we compactify S1 with center stabilizing deformation. And the other is the 2D center vortex semiclassics, where we compactify T2 with soft flux. And in this case, monopole causes confinement. And in this case, center vortex causes confinement. So the natural question is how to relate them. So we consider interpolating setups between them. So to interpolate them, let's consider SN Yamil theory on R2 times S1 times S1. And we add center stabilizing deformation to the S1 force, and we add Toft flux on this S1 times S1. And let's take L4 small and vary the size of, let's take this, the last S1 small, and vary the size of S13, L3. Then in the decompactification limit of S13, then this setup would approach to the 3D monopole semiclassics. And on the other hand, if L3, if S1, if third S1 is also small, then this setup is very close to the center vortex semiclassics. And here we have extra center stabilizing deformation on S14, but the Toft flux, as we saw, the Toft flux already stabilizes the center symmetry on these two S1s. So in this case, in this limit, the center stabilizing deformation on S1 force does just nothing. So this setup connects this framework and this framework. And here are main claims of our work. We will see the setup is this one, and we will so because L4 is small, so you can consider 3D effective theory on R2 times S1. And yeah, here are main claims of our work, and we will see that the 3D effective theory on R2 times S1 is smoothly reduced to 2D center vortex gas as we make S13 smaller. And second, so this is a continuity in the level of effective theory. And second, you can consider the BPS or KK monopole in this compactified setup. And from the 2D perspective, this is actually the center vortex instanton on R2. So you can consider the BPS or KK monopole in R2 times S1, and it is the center vortex, which has not been known in the center vortex semiclassics, but this can explain the center vortex in 2D. Okay, so let's see the first one. So as I said, because we take L4 small, so you can consider 3D effective theory on R2 times S1. And as before, the 3D effective theory is just 3D abelian gauge theory, Cartan abelian gauge theory plus monopoles. But here the geometry is R2 times S1. And the tricky one is Toft flux inserted here. And this causes the twisted boundary condition, which we call shift twisted boundary condition. Let me add some words on it. Well, when we derive the abelian gauge theory, we often work on this gauge. Polyakov loop is the clock matrix. And in this gauge, let's remember how to insert the Toft flux. Here is how to insert Toft flux. And to insert the Toft flux, you can take shift matrix and clock matrix as transition functions. So in this gauge, the transition function for S13 is the shift matrix. And in terms of real algebra, this is wide permutation. This acts as a wide permutation for the dual photon. In other words, in the 3D language, the Toft flux in 4D is translated as a 3D GN twisted boundary condition. And this acts on the Polyakov loop. And if we change the Polyakov loop as the center element, then if we multiply the center element to the Polyakov loop, then the basis is permuted. So this is also called the wide permutation for the dual photon. But anyway, in the 3D effective theory on R2 times S1, the 3D effective theory on R2 times S1 can be written like this. 3D abelian Cartan gauge theory plus monopoles on R2 times S1 with some twisted boundary condition. And from this effective theory, you can derive the center vortex gas expression. Let's make L3 smaller than the dynamical scale. Then the dual photon is frozen to this zero mode of the twisted boundary condition. And actually, this zero mode only has n solution, or n discrete solution. This zero mode equation of twisted boundary condition has only n discrete solution. So the partition, so let's consider the partition function of 3D effective theory. Then if the L3 is small, then where the partition function can be approximated by the discrete sum of these zero modes. And from the monopole term, you can derive this expression. And this is nothing but the 2D center vortex gas partition function. So therefore, this setup explains a smooth crossover from 3D monopole gas to 2D center vortex gas. Well, and let me add something. In terms of the vacuum, this effective theory, this effective potential, monopole induced effective potential has n extrema, and this extrema of the monopole potential is actually this n vacuum. So although this twisted boundary condition, while this twisted boundary condition kills a lot of degrees of freedom, but this twisted boundary condition preserves the vacuum. So this explains the smooth crossover from 3D monopole gas system to 2D center vortex gas system. Okay, next, the second stuff. Then next move on to the second stuff, which is how monopole and center vortex are related. Well, to see how monopole emits magnetic flux in the 3D perspective, we solve the classical equations of motion with this twisted boundary condition. And you can solve, you can actually get, it's guess, but you can solve the classical equation of motion with twisted boundary condition by mirror image. So actually, the infinite chain of BPS and KK monopoles like this is the solution. And this solution explains the following configuration. The alpha I monopole emits a magnetic flux 2 pi alpha I, and you can rewrite the 2 pi alpha I as 2 pi nu I minus 2 pi nu I plus 1, where these are weights of defining representation. And so let's suppose that the outgoing magnetic flux is 2 pi nu I going, and it goes upwards. So this magnetic flux goes upwards, then it is subject to the shift twisted boundary condition. And since this is shift twisted boundary condition, where its color is shifted. So due to this twisted boundary condition, the magnetic flux 2 pi nu I becomes 2 pi nu I plus 1. So due to this twisted boundary condition, this magnetic flux becomes this magnetic flux 2 pi nu I plus 1. So incoming flux is 2 pi nu I plus 1 comes from the bottom. So this is a situation of how monopole emits a magnetic flux. And also from this solution, you can read that the magnetic flux is localized in the 2D perspective. Its size is approximately order n times L3. It is localized in the 2D. So you can treat it as a localized object in the 2D language. And yeah, as a side remark, there are n species of monopole, BPS and n-1 BPS monopole and 1 KK monopole. So there are n species of monopoles in the 3D effective theory, but they can be unified by extending the X3 moduli. Okay, so let's put monopole alpha I here, and let's move this upwards. Then after the shift twisted boundary condition, the alpha I monopole transmutes to alpha I plus 1. So although in the 3D semiclassics, there are n species of fractional instantons, but in the 2D, they are unified to be one species of fractional instanton. And finally, this configuration has all desired properties of 2D center vortex instanton. So let's measure the magnetic flux of it. And as I said, the magnetic flux is these ones. And actually, if we wind the Wilson loop around this magnetic flux, then you will get the center element. So these magnetic fluxes is what we call the center vortex. These are center vortex-like magnetic flux. So let's look this in 2D perspective. Then this is fractional instanton, and this rotates a Wilson loop by a center element. So this is indeed the center two-dimensional center vortex instanton. So although we have seen two ways to describe confinement semiclassically, but actually they are essentially the same. And also, this picture shows monopole as a junction or kink of this center vortex-like magnetic flux. This realizes the old expectation. This realizes the expectation in the old literature. So let me summarize. The traditional clock confiners are monopole and center vortex, and corresponding to these clock confiners, there are two frameworks to understand confinement semi-classically. One framework is to S1 compactification with center stabilization, and then we can realize the situation where the monopole gas causes confinement. And the other one is a 2D center vortex semi-classics where we compactify T2 with soft flux. And in this case, we can realize the situation where the center vortex gas induce confinement. And in this work, we bridge them, this framework and this framework, by considering interpolating setup. And we found that monopole instanton in 3D effective theory, monopole instanton in 3D setup, and the center vortex instanton in 2D setup are well, essentially the same. And if we look closer at the monopole in R2 times S1, then we can see monopole appears as a junction of center vortex-like magnetic flux. That's all. Thank you very much.
Thank you very much. So, questions or comments?
To see the monopoles, you had to add double trace deformations, right? To see the
Yeah.
monopoles.
This is, well, this is double trace deformation.
Yeah. And on the other side, you don't have double trace.
Yeah, right.
So it's not clear if it's really the same because you write equal sign, but it's in different theories.
Yeah, they are different theories, but you can connect them with this setup.
What do you do with the double trace though?
Where in the 2D semi-classics, the
Oh, it doesn't matter at this point.
flux
Okay.
already stabilize the center.
Yeah, so you can add them or it doesn't matter. You can add them or not add them. It doesn't do anything.
yeah, right,
Okay.
right.
Yeah. Okay. Thanks.
So, other questions or comments?
Can you evaluate the one loop beta function from this picture somehow?
One loop beta function,
Mm.
where after abelianization, where the product group is fixed to the center symmetric value and the abelianization occurs. And after the abelianization, then the coupling doesn't run.
Mm. I see.
So yeah.
You cannot include some next leading correction in some systematic way because you are in the very end of the weak coupling region, right?
Yeah.
And then cannot we approach to the inside of that region?
I
Somehow.
see.
I don't know.
Yeah, we want to do that, but yeah, it's difficult. we have to remember that there are many higher culture crime modes, so yeah, it's difficult.
So,
do you have a comment about index theorem
Index theorem on
I see index theorem is related about BPS and Karzak line. in this case, some relation of index exists.
Sorry, what is your question? Your question is on R3 times S1 or R2 times S2?
Yes. The BPS and KK.
BPS and KK monopoles?
Yes. In my understanding, there are some relation about index, but in this case, some index.
Yeah, here we consider pure Yamil theory, but if there are fermions, then from the index theorem, the BPS or KK monopoles can carry the fermionic zero mode.
I see.
Yeah, but yeah, here we focus on the pure Yamil, just bosonic.
Thank you.
The questions. Okay, let's thank to Yui again.
Thank you very
Thank you
much.
very much for